Welcome to lecture number 25 for ECE 341 Random Processes. This and the next lecture look at the student t-test. So if we go back to the syllabus for this course, ECE 341, where we're at is we've gone through combinatorics, discrete probability, continuous probability, Markov chains. Now this last section, we're looking at data analysis. Probably the most important part of the course. When you go into lab and collect data, every time you collect data, you're going to get different answers. It's a random process. How do you analyze the data? Well, that's what we're going to look at in the next couple lectures, and there are actually thousands of different tests you can run. We're just going to look at three of them: t-test, chi-square test, and f-test. T-test is a test of a mean. It's probably the main test you're ever going to use. Test of mean would be like, I've got a battery, how much energy is in the battery? I've got a light bulb, what is the life of that light bulb? I've got a product coming off the assembly line, what is the weight? What's the gain of a transistor? What's the resistance of a resistor? Those are all t-tests. A chi-square test is a test of a distribution, such as, is a die fair? Is the distribution of a resistor uniform, normal, or whatever? That's a chi-square test. An f-test is a test of the variance, such as, do two different populations have different variability, different variance? Is the spread greater? That's an f-test. So that's kind of where we're heading. The first four lectures look at a t-test. This and the next lecture look at a t-test for a single population. Then we'll look at a t-test for two populations, basically A versus B. So, a little bit of background. In this course, we're covering several different ways to calculate probabilities. And to give us something concrete to think about, suppose I'm rolling dice. I'm rolling four four-sided dice, three six-sided dice, two eight-sided dice, taking the sum. And I want to know something about the die rolls. Like, what's the probability of getting 35, probability of getting more than 35, or what's the 90% confidence interval? Now, where that applies in industry is you've got a product coming off the assembly line. I want to know what's the weight, what's the probability that the weight's going to be more than 2 pounds, what's the 90% confidence interval for the weight. I've got a transistor, what's the gain, what's the probability the gain's at least 100, what's the probability the gain's between 100 and 300, that sort of thing. So let's just look at the dice as an example, something to refer to. Now, in this course, we've covered a couple different ways to calculate probabilities. One approach is Monte Carlo. With Monte Carlo, what you do is you repeat an event over and over again, such as roll the dice 1,000,000 times, and simply count. How many times do I get the number 35? How many times do I get the numbers bigger than 35? Or how many times, what's the 90% confidence interval? So you can do that. For example, if I roll the dice 1,000,000 times and count, how many times was the sum equal to 35? I got 4.44%. So for Monte Carlo, that's roughly the odds of getting 35. I can count how many times the sum was bigger than 35. And there that was 15.85%. That's roughly the odds of getting more than 35. And I can also sit there and find out where the low 5% are, where's the high 5%, find the area in the middle. That's your 90% confidence interval. So experimentally, I got 90% of the rolls are between 21.5 and 36.5. That's Monte Carlo. Monte Carlo is nice because it doesn't really take any knowledge of statistics, but it can be expensive. If, for example, it cost $1 to roll the dice each time, that just costs $1 million. So sometimes that's just not practical. Second way to get the odds is I can calculate what they are. I can do that using enumeration, convolution, combinatorics. I'll give you the same answer. Those are all topics we talked about in this class. The problem with calculating the odds is you have to know the distribution. Sometimes you just don't know what that is. I've got a product coming off the assembly line. I want to know how much it weighs. I don't know what the distribution is. That's what I'm trying to find out. So sometimes calculations work great, sometimes they don't work at all. A third approach was the normal approximation. This uses the central limit theorem. The central limit theorem says most distributions converge to a normal distribution, so I can use that. I know what the mean and variance is for each, like a 4-sided die, 6-sided die, 8-sided dice. Therefore, I know what the mean and variance is for y, the sum of 4-sided dice, 3 6-sided, 2 8-sided die. Once I know the mean and variance, I can use the normal distribution and calculate different probabilities. So for example, if I want to know what the probability is of getting 34.5, I can just find out the z-scores for, well, for 34, I'm going to take, actually for 35, I'm going to go from 34.5 to 35.5, take the area between those two, which I can do in MATLAB. I find the z-scores, distance to the mean in terms of standard deviations. There's the first z-score, area of the tail. Here's the second z-score at 35.5, area of the tail. Take the difference, there's your probability. So that's roughly the probability of rolling 35. I can find the probability of rolling numbers bigger than 35, in which case I'm going to look at the number 35.5 on up, which would be right here. 88% are less than 35.5. 1 minus that, 11.15% greater than that. I can find the 95% confidence interval. For there, I would use a normal distribution, find out how far you have to go for the tails to be 5%. That turns out to be 1.64485 standard deviations. I'll then go left and right of the mean by that many standard deviations, and it tells you that the 90% confidence interval is between 21.4 and 37.6. That's all things I can do with the normal distribution, stuff we covered earlier in this course. The problem with the normal distribution is I need to know the mean, I need to know the variance. But if I know that, I can actually get the same results I got before, but here I just calculate it. I don't have to actually roll the dice. If each experiment costs money, this is free. And the results are pretty much the same. Monte Carlo is 4.43%, normal approximation 4.34. Probability greater than 35, 11.39 versus 11.15. Confidence interval 22 to 37, 21.4 to 37.6. But the number rolls, 1,000,000 versus 0. So there the normal approximation is really nice. But again, that assumes that I know what the mean and variance are. So here's the problem. This is what leads into this lecture and the t-test. What happens if you don't know the PDF of what you're measuring? I don't know the mean, I don't know the variance. But I can collect data, like I can roll the dice. Can I find the probability of rolling of 35, probability of rolling more than 35, or two-sided test, what's the 90% confidence interval just from those measurements? And the answer, of course, is yes. What you wind up with is a student t-distribution. Now, what the student t-distribution assumes is that you have a normal distribution to start with, and that's usually the case. What I'll do is I'll go and collect n samples, kind of similar to Monte Carlo. Monte Carlo, I rolled the dice 1,000,000 times. With the t-test, I don't have to do 1,000,000 rolls. I could just do maybe 20, maybe 100 rolls. From those samples, I'll estimate the mean and the variance. And the result is a student t-distribution. It's very similar to a normal distribution, but it takes sample size into account. So if I have a normal distribution like this, if I just have a sample size of 2, I have to be kind of cautious. It's basically a normal distribution where I expand the tails up. If I only have a sample size of 2 and I want to bet on something, I'm going to be kind of cautious. So increase the tails, make you more cautious to reflect the sample size. As sample size goes to infinity, the t-distribution converges to a normal distribution. And a normal distribution and a t-distribution, the calculations are almost the same. With a normal distribution, the mean is just the average of the data. The variance is the average distance to the mean squared. And the z-score is the distance to the mean in terms of standard deviations. That's if you have a normal distribution. That's if we have a known mean, no standard deviation, or I've sampled the entire population. A student t-distribution is almost the same. The mean is still the average, but that's called x bar. It's because I have a sampled average rather than the population's average. That's what the different symbol means. This is for a population. This is for a sample. The variance is almost the same. It's the distance to the sample mean squared. But instead of dividing by n, I divide by n minus 1. So this is kind of a subtle difference. And there is another term called degrees of freedom. That's the sample size minus 1. With the t-distribution, I have to keep track of the sample size. A sample of 2 is different than a sample of 1,000. That's what the degrees of freedom does for you. And then to calculate probabilities, I use the t-score. That's almost exactly the same as the z-score. It's distance to the mean in terms of standard deviations. The difference, however, is this is the distance to the sample mean divided by the sample standard deviation. Almost the same as z, but again a little bit different because it's the sample mean, sample standard deviation, rather than the population's mean, population standard deviation. A second thing that's slightly different with a t-distribution is the t-table. So this is kind of like a normal distribution table. This is the area of the tail, just like a normal distribution. This is your t-score, very similar to a z-score, but I also take population or sample size into account. And kind of what you notice is, let's take a number like 1%. If I want 1% tails, the t-score, as sample size goes to infinity, this becomes a normal distribution. So at infinity, this becomes the normal score, the z-score. As the sample size gets less than infinity, the number increases. And that kind of makes sense. Kind of think if I'm going to Vegas and I'm going to bet on the result of something, if I don't know the mean, I don't know the standard deviation, but I can collect data. If I have a sample size of 2, the degrees of freedom is sample size minus 1. Sample size of 2, I'm going to take the mean and go plus minus 31 standard deviations. That'll give you the 98% confidence interval. If I have a sample size of 3, I've got a lot more data with 3 versus 2. I can be less cautious. Sample size goes to 4, 5, 6, and so on. So the t-score drops, meaning the confidence interval keeps on shrinking down and down with the sample size. It will never get smaller than the actual variation in the population. So the t-score converges to a normal distribution as sample size goes to infinity. That's where it converges to, but I take sample size into account, so I'm more cautious with a small sample and converge to normal distribution as the sample size goes to infinity. That's the t-table. In addition, you can go to StatTrack. So for example, this is StatTrack, one of the best websites for statisticians. Scroll down, it's got a bunch of different tests. You can do binomial, chi-squared, F, all stuff we'll be doing later on. We looked at a normal distribution before. This is a t-distribution. With a t-distribution, you input here. If use the option, the t-score. I can find the area of the tail to the right, in the middle, so on. Here we're just doing the area of the tail. The degrees of freedom is sample size. So if I have a sample size of 10, that means 9 degrees of freedom. If my t-score is minus 1.5, this is the area to the left of minus 1.5. 8.3%. As the sample size goes to infinity, this becomes the z-score. So a normal t-distribution converges to a normal distribution as sample size goes to infinity. Thing to note though, if I have 1 degree freedom, that means I have a sample size of 2. I can calculate a probability. If I have a sample size of 0, meaning sample size of 1, you get an error message, sample size of 1 is meaningless. You have to have at least a sample size of 2. So that's one way to use a t-table. I can also go the other way around. If I want to have the probability being 5%, here's the area of the tail. And again, as sample size goes to infinity, this converges to a normal distribution. That's the number we saw before. 5% tails has a z-score of 1.64486. T-score is a little bit different as the sample size gets smaller. So here's a sample size of 1,000. A little bit bigger, sample size of 100. Just a hair bigger, sample size of 10. And sample size of 2. That is StatTrack, a convenient way to calculate t-scores and probabilities for a t-distribution. Okay, a note on t-tables. Again, this is the sample size minus 1. That's the degrees of freedom. That minus 1 kind of reminds you that you need at least a sample size of 2 to have anything meaningful. Sample size of 1 tells you nothing. Another way to think about that is I'm trying to determine 2 parameters from a population. I want to know the mean and the variance. In order to get 2 measurements, I need 2 data points. If I have a single data point, I can't estimate 2 parameters with a single data point. I need at least 2. So this sample size minus 1 is kind of a reminder you need at least 2 data points. Also note that the t-score gets smaller as the sample size gets bigger. I can actually get results with a sample size of 2. I've got to be pretty cautious with a sample size of 2, but I can actually do something. That's all I really need. Sample size of 3 would be nice. The t-score drops quite a bit. 4 is even better. 5, 6, 7. Then I get diminishing returns. So, kind of surprisingly, I don't need a sample size of 1,000. I can do pretty good with a sample size of, maybe 10, maybe 5. That's actually really good in industry. Oftentimes, you just don't have a whole lot of data. For example, I worked at a company where they would take products that were returned and try to gain information from them, like is something wrong with our manufacturing process. Now, in that case, you would like lots of data because more data makes it easier to analyze. But then these are return products. You would like to have 0 data. So actually, a few products would get returned, not very many. But you're kind of stuck as a statistician. You only have the data that's coming in. So you might have 2, maybe 3 data points to look at. Get kind of excited when there's 4. Just a little bit of data is all you have to work with. And with a t-test, that's really all you need. I can actually tell you something with a sample size of 2. 3 would be nice. 4 even better. So to illustrate that, let's go back to our rolling dice. I've got a bunch of dice. I'm going to roll them and see what the results are. Now, if I don't know what the probabilities are, I'm going to collect some data. So here I roll the dice, or in MATLAB, I generate random numbers. Here's my 4-sided dice, 6-sided dice, 8-sided dice. Add them all up, I get the roll. Suppose I get the number 30. From that result, what's the probability of getting 35? What's the probability of getting numbers bigger than 35? And what's the confidence interval? Well, to do that, I need to find the mean, the variance, degrees of freedom, and so on. So here's the calculation. The mean is just the average. The average of 30 is 30. The variance is the distance to the sample mean squared divided by a sample size minus 1. And what I get is 0 squared over 0. That's 0 over 0. That's undefined. If you get an answer like that, the math is trying to tell you something. When you get 0 over 0, the math is telling you something. The challenge is trying to figure out what the math is trying to tell you. In this case, what the math is telling you is that a sample size of 1 is meaningless. I cannot do data analysis with a single data point. I need at least 2. Okay, so instead of just having single data points, suppose I roll the dice 3 times. I do that, I get 3 numbers, so here's my results. 30, 40, 28, found in MATLAB. With that data, I can then do some analysis. I want to find out what is the mean, what is the variance, what's the sample size. And in MATLAB, there's commands standard deviation and variance. Actually, if I look at these two, this is actually using the sample. This is 1 over n minus 1. So this is the variance, s squared, times the sum of x minus x bar. This is what MATLAB does. That's the MATLAB command variance, is this. This is MATLAB command standard deviation, std. MATLAB assumes this is a sample. When you calculate mean and variance, it actually doesn't do the, roll back a little bit. It doesn't calculate this mean and variance. MATLAB actually calculates the sample mean and variance. It assumes I have data from a sample, so this is how it calculates it. If you actually want to know the population's mean and variance, I have to scale it. It should be 1 over n rather than 1 over n minus 1. Or I can do this calculation by hand. Just kind of a subtlety. So in MATLAB, I actually don't have to worry about that n minus 1. That's done automatically when I use the MATLAB command std or var for variance. So this is the sample mean. That's the sample standard deviation. Once I get those numbers, I can start doing a t-test. So for example, if I want to know what's the probability of getting the number 35. So here's the number 35. I do the same trick I did with the normal distribution. I am using a continuous distribution, a t-distribution, to approximate a discrete probability, 35. What I'm going to do is interpret 35 to be the area between 34.5 and 35.5. So to do that, I calculate the t-score at the left-hand point, 34.5, how far that is from the sample mean in terms of sample standard deviation. It's 0.28 deviations. Find the t-score at the right-hand point, 35.5. Go to a t-table, in this case, StatTrack. I've got 2 degrees of freedom. Here's the t-score. Input the t-score. It'll calculate the probability. And the left endpoint, the probability is 40%. The right endpoint, area is 35%. Take the difference, 4.4%. So based upon a sample size of 3, I should get a 35, 4.4% of the time. And what's kind of neat about this is you go back to the data. This is all I'm working with. Given those 3 numbers, what's the probability of rolling 35? Now that's not really obvious from that data, but using the central limit theorem, t-distribution, I can calculate the mean, standard deviation, sample size, use a t-table to tell you what's the area between 34 and 35, and I almost got it. That's actually a really, really good result. Again, if you try this yourself, you're going to get different answers. I only have a sample size of 3. But with just a sample size of 3, I almost nailed the probability of getting 35. Partly that was luck. Partly that's a t-distribution. What's the chance of getting numbers bigger than 34.5? And here, what I really want is numbers 35 or higher. Next, let's find the probability of rolling a number bigger than 35. So here again, I'm going to interpret this. This is a continuous distribution approximating a discrete distribution. I want the numbers bigger than 35, so I want the numbers 36 and higher. What I'll do, since this is continuous, I'll interpret that to mean numbers bigger than 35.5. So to do that, I'll find the area of the tail. To do that, I'll find the t-score. How far is 35.5 from the sample mean in terms of sample standard deviations? And I'm 0.4407 standard deviations away. That's the t-score. Then using StatTrack at 0.4407, get my adds. I'll go back and say here's the t-score. I've got sample size of 3, meaning 2 degrees of freedom. The t-score was 0.4407. 0.4407. Here's the negative, because that gives me the area of the tail, area to the left. Two degrees of freedom. That's 0.4407. Calculate. And poof, there's the answer, 35%. Now it really should be 15%, so I'm a little bit off. Not too surprising that I'm a little bit off. I only have a sample size of 3, but it kind of gives me an idea what the probability is. To get the 90% confidence interval, I go to a t-table, and for 5% tails, what I'll do, I have 2 degrees of freedom. I want the tail to be 5% for a 90% confidence interval. Gives me 2.9199. That tells me I need to go 2.9199, 2.92 standard deviations left and right. So for the sample mean, going left and right, 2.92 standard deviations tells me the 90% confidence interval is between 13.89 and 51.4. The correct answer is 21.5 to 38.5. That's using enumeration. So I'm a little bit off, but again, I only have a sample size of 3. So the results, comparing Monte Carlo to a normal to a t-test, the probability of hitting 35 is almost the same. Probability numbers bigger than 35 is a little bit off. 90% confidence interval is a little bit off with the t-test, but the number of rolls. Monte Carlo took 1,000,000 rolls. Normal approximation took 0, but then I had to know what the mean and standard deviation are. If I don't know that, I can use a t-test. With only sample size of 3, I'm getting numbers that are reasonably close. More samples would give me better data. To illustrate that, I'm not going to go through all the data, but repeated the previous experiment with 10 rolls, with 30 rolls, and here's what I got. Again, if you ran this yourself, you're going to get different answers. It's a random process. With 10 rolls, I got 3.75% chance of 35. 30 rolls, 4.27, getting closer and closer. When I get to infinity, it'll be the same as a normal approximation. Probability of getting numbers bigger than 35, 40%, 18%, 14%, and getting closer. Correct answer is 15.8. Confidence interval should be 21 to 38. I'm getting 13 to 41, sample size of 3, 18 to 39, pretty close, sample size of 10, 22 to 37, sample size of 30. And if you compare that to a Monte Carlo, I rolled the dice 1,000,000 times. Here we just need to roll it 3, 10, 30. 30 is pretty good. I don't need 1,000,000 rolls. I can get really good results with only 30 samples. So this kind of leads to a question. What kind of sample size do I need? You really don't need that large of a sample size. And you've probably seen this if you watch the news. There's all sorts of polls. There's the ABC News, Washington Post poll, CNN polls, Pew polls, so on. Oftentimes these polls are just using a fairly small sample size to represent a large population. For example, The 2023 ABC News poll tried to find out what's happening in the opinion of 350 million Americans. Well, that's a national poll. I don't need to measure 350 million people. They got results using only 1,006. During elections, like the election in 2024, there are 5.6 million people in Michigan who voted. The poll only sampled 726. 7 million people voted in Pennsylvania. The poll only sampled 819. 3.4 million voted in Wisconsin. The poll only sampled 736. You don't need a huge sample size to get a good answer, to get good results. That's a t-test. As a caveat, however, when you do collect your data, the data needs to be random. It can't be biased. And this has caused problems in the past. For example, during the Great Depression in the 1930s, a poll went out to find out how many people were out of a job. And people were pretty sure that the country was hurting. You'd see people standing in line looking for jobs. However, the result of the phone poll was that everybody had a job. So what happened? Well, it turns out that if you lose your job, you have to cut your expenses. One of the first things that goes is your telephone. You don't need that monthly expense for a telephone. So what they found is that when you call people on the phone, surprise, surprise, the people that have jobs have jobs. So really all they were doing is finding out how many people that have telephones have jobs, and it was like 100%. That was a biased survey. They didn't sample people that didn't have phones. And likewise got a nonsense answer. Another example where polling got it wrong is the 2016 primary between Bernie Sanders and Hillary Clinton. Now, the polling up until the primary was predicting that Hillary Clinton was going to win. So the night of the election, Bernie Sanders left, went down to, I think it was North Carolina, to keep campaigning, and was kind of surprised when he found out that he actually won. In fact, he didn't even have a victory speech ready to go. That result surprised everyone, including the candidates. Well, the problem with that poll is they were doing telephone polls. The way you get the telephone numbers is you go to the phone book. The phone book lists the phone numbers of landlines. It doesn't list the phone numbers of cell phones. Well, it turns out that older people, like me, we own landlines. Younger people have cell phones. So when you use the phone book to find telephone numbers, you're only sampling the older voters that have landlines, and the older voters who are voting for Clinton, the younger voters who are voting for Sanders. So the result of that poll got it wrong. That's another example of a biased survey. So how do you make sure your survey isn't biased? Well, that's actually a really hard problem. There are courses that you can take on that. Probably the options in political science. It's one of the reasons that pollsters are highly skilled professionals. Now, for example, if you look at the 2023 ABC News Washington Post poll, they explained at the end their methodology. They surveyed people both in English and Spanish. They didn't want to have a bias for one language. They surveyed 1,006 adults. That's to represent 350 million people. But they had to make sure that of those 1,006 people, it was 25% Democrat, 25% Republican, 42% Independent, trying to avoid a bias in the polls. If the polls don't match the national percentages, you might have a polling result or biased result. And even then, polling isn't easy. When you poll people, not everybody responds. Well, if it turns out that you have a disproportionate number of one party responding versus the other, that's going to bias your results. So professional pollsters have to take the data and weight it so that you have equal representation or proportionate representation of different groups. How you do that is kind of an art form. It's part of the reason that accurate polling is a highly developed, highly skilled process. There's a reason people say at the Pew Research Center are highly skilled professionals. It's not trivial. So that's kind of my idea of a t-test. Now, the answers with the t-test are slightly different if you're talking about a population versus an individual. For example, if I roll dice, every time I roll the dice, I get a different answer. That variability is going to stay there no matter how many times I roll the dice. For an individual, the variance is just the distance to the mean squared divided by sample size minus 1. That's the MATLAB command variance. For populations, however, the variance drops by sample size. When I roll dice, there is an average. As I roll the dice more and more, I have a better and better idea what that variance is, or what that average is. So what happens is, if I'm looking at populations, the variance drops with the sample size. So eventually, I get a tighter and tighter confidence interval. Eventually, I know precisely what the population's mean is. So if you want to know something about an individual, you don't divide by n. If you want to know about the population, you do divide by n. So there's kind of a slight difference in the two. Depends upon which one you're talking about. So for example, suppose when I roll dice, I've got my 4-sided dice, 6-sided dice, 8-sided dice, add them all up. What is the average for that die roll? Well, the average is just a number. I'm trying to estimate what that number is. I don't know what it is, but I can give you a confidence interval and bound it based upon my measurements. As the sample size goes to infinity, eventually I know what that mean is dead on. So for example, as I increase the sample size, I get a tighter and tighter bound for what that mean is, and that's for two reasons. One is the t-score gets smaller and smaller as sample size goes up. In addition, I divide the variance by n, or divide the standard deviation by the square root of n to get my confidence interval. So as n gets larger and larger, the confidence interval gets tighter and tighter, until eventually I get 29.5 is the exact mean. That's the actual average of these die rolls. I know what that is because I know what the mean is for each die. If I don't know that, I can calculate what that is, at least a bound for it. And with 3 dice, actually with 1 die, I have no idea. I need at least a sample size of 2. With 3 dice, I know that the mean of that die roll, the mean of y, is somewhere between 23 and 44. If I have 10 dice, I'm between 25 and 31. It's getting tighter. 100 dice, between 28 and 29. 1,000 dice, between 29.2 and 29.8. And eventually, I'll get the mean is actually 29.5. So sample size goes up. Eventually, I know what the population's mean is. So this causes kind of a problem for students. When do you divide by the sample size? When don't you? That's kind of subtlety. It depends upon the question you're asking. Depends upon, are you asking about an individual or a population? An individual, there's always variability in the die rolls. If I want to know, like, what number am I going to roll next time I roll the dice? If I'm doing like poker, I'm going to deal out 100,000 hands of poker. How many of them will be a full house? That is a binomial distribution. It's got some spread. That spread doesn't change with the sample size. If I keep on repeating over and over again, I eventually get the correct spread, but the spread is always there. This is an individual. I'm going to say deal out 100,000 hands one time. If I do that, I don't divide by n. That variability is always there. The variance converges to the population's variance. The sample size goes to infinity, but it doesn't go to 0. A different question. What is the probability of being dealt a full house? What is the average of rolling those dice? That's a number. I may not know what that number is, but it's just a number. As the sample size goes to infinity, I can get a tighter and tighter bound on what that number is. In that case, I do divide the variance by the sample size. So you have to kind of look at the question. Am I asking about an individual? Should the variance go to a constant? Or a population? Should the variance go to 0 as sample size goes to infinity? So that's kind of a t-test. If you want to know what's happening on your assembly line, you need data. If you can measure everything, just use enumeration. That way you know exactly what you're producing in industry, but then you have no product to sell because you've tested everything, everything's used. I could use a Monte Carlo simulation. That gives you good results, but you need a huge sample size like 1 million. It can be very expensive. If I know the mean and I know the standard deviation, then I don't really have to do any measurements. I can just use the normal approximation and get pretty good answers. Typically, I don't know the mean, I don't know the standard deviation. That's what I want to know. I've got something coming off the assembly line. What is it? That's when you use a t-test. For a t-distribution, I need a sample of at least 2, but I don't need millions. A sample size of 10 is actually pretty good. Sample size of 100 is great. Gallup, for example, uses a sample size of 700. That's to estimate what's happening with 1 million people, 7 million people. So you don't need a huge amount of data. And that's what the t-test gives you. But you do need at least a sample size of 2. So that is lecture number 25, t-distribution. The next lecture, we'll go through a couple examples of t-distribution with one population. Lecture 25 for ECE 341.